mean, this is really a difficult spot to present a little technical talk. It's 3 p.m. after lunchtime, and we will deep dive a little bit of mathematics. We'll try to keep it at a high level, but bear with me. Yeah? Okay, so I think thanks for the nice introduction, and then maybe we can get started with the presentation. How do I start? Oh, okay. Okay, so yeah, so today's talk, I will be talking about the role of a Bayesian optimizer in well location optimization space. Don't worry, we will go probably the term by term. I'm very sure that a lot of people here may know Bayesian optimizer well, but may not know what exactly this well location optimization problem is all about. We will go slowly, we have 1 hour, okay? So, this is a cautionary note. We are requested to show that. I'm very sure no one can read that from that distance, but it's a mandatory slide we need to show. Today, okay, so what I plan to cover and might help you whether you want to sit or leave from the back end gate. Little bit about the shell journey, but I think Karthik in the morning did a very good, fantastic job in helping explain or helping make you aware the shell's digitalization journey, right? But for the people who missed the morning sessions, what I will do maybe is will still probably share a couple of slide information in that space as well. Then we'll move to the problem motivation, right? What exactly we are trying to solve in well location optimization space. And a little bit about kind of a tutorial session on the Bayesian optimizer. I hope you like that as well, which I tried in my department and they enjoyed, so I thought maybe that might also help you a bit. And our performance challenge, when we try to integrate that Bayesian optimizer technique in our well location optimization, what are the performance challenge we felt, and ultimately results and conclusion. Okay, with the slide about, so first of all, I'm very happy and proud to be here in Cypher 2023. So I believe the next decade, the 10 years, would be shaped by 2 main trends, 2 mega trends. One is energy transition, and another is digitalization. These 2 technologies are going to have a profound impact in our lives. And we have an urgent challenge to also address. One, about the climate change, the net zero emission energy system we all thrive to reach, Paris Agreement. And second, there is also a huge growing demand for the energy. How do you solve this optimization problem without the help of digitalization? So I think the technology innovation and then digitalization is a key enabler to kind of move into this energy transition journey. Okay, so this is about the Shell's powering progress strategy, right? What we feel or what we have seen, right? Digitalization playing key role in our powering progress strategy as well. What are those? One, of course, generating the shareholder value, right? Second, achieving a net zero emission system. Can I see those slides? Yeah, okay, I can see my slides here as well. Net zero emission systems. Third is powering lives. Fourth is respecting nature, right? While doing everything, not really, respecting the nature is an important thing. Digitalization is playing crucial role in kind of helping optimize our lot of operations, assets, and generate the shareholder value. Digitalization is also helping us in our net zero emission scope 1, scope 2, scope 3, right? Reducing our own emissions, helping our consumers, customers provide the energy which is of a low carbon emission, and also producing a new technological solutions in this space. Powering lives, I can give you an example which probably you guys can connect. There is a startup called the Kabadiwala Connect. You might have heard, the Chennai-based startup. That's the powered by Shell's Game Changer program in helping develop the digital platform for the Kabadiwala Connect, right? And that basically helps improve the life of waste workers. The third is respecting nature. So there are many examples. I'm just kind of sharing a couple of examples which probably you guys can connect quickly. The respecting nature, the Shell and the University of Glasgow is having a collaboration to build a software product which kind of helps monitors the spatio-temporal analysis of data for the groundwater management. And that's being used by a lot of governmental agencies across the globe. With that, maybe let's move on to the little deep dive into the few of the applications and then get to the topic of today's discussion. So as I said, right, a lot of technologies in the AI and machine learning space are helping generate the value for a shell, reduce the cost, right? Driving efficiency through our existing businesses. Predictive asset maintenance. 3 trillion of the data points basically are observed by machine learning technologies to detect anomalies. Yes, you heard it right, 3 trillion data points, right? And we call it as a predictive asset maintenance technology. I think you guys are quite familiar with that as well, right? Real-time production optimization technologies developed with the help of external technology provider called C3. Digital twin, everyone is familiar. We have deployed almost around 5 different assets, the digital twin technology, and that is driving our efficiency by enabling the remote operations, automations, and improving the collaborations. Okay, the subsurface, I'm kind of connecting the driving efficiency through different technologies now to the subsurface. There are 2 key problems in the subsurface, or the 2 key challenges in the subsurface. Yes, we hold a lot of data, but the data is still, right, not very easily accessible to the geophysicist. In the past, geophysicists used to kind of spend 70% of their time in kind of bringing the right data set in the right shape for their analysis purpose. What we did from 2017 onwards, started building the subsurface data universe, which is a cloud-based platform, kind of brings all the data together to have a global access and bring the value out of it. Second challenge is having the workflow. In the subsurface space, I'm not very sure how much familiar you guys are with the subsurface technologies, but I think the workflows which we kind of operate, even not only Shell, but most of the energy companies, they are quite old, right? 50 years old, and we have same workflows which we kind of run. We have bits and pieces adapted with the newer technologies, but the workflows are same. What we are trying to do here, trying to take a help of deep learning technologies to kind of improve the efficiency in the workflows. One of the first applications of machine learning is understanding the seismic image interpreted to understand the salt and fault crawler things. The last, of course, the topic of today's discussion, I took maybe 10 minutes to come to this point. So well location optimization. We are using the AI technologies to understand where to drill next. Yeah, I won't spend more time on this slide now, but let's move on to the next. Okay, coming to the problem motivation about the well location optimization problem. Right, so I thought of taking a help of my leadership to explain you what this well location technology is all about. Let me see if I can play this video. Yes. Can I play can I take a pause? I'm not very sure. How do I? Okay, sorry. I think we need a couple of minutes to connect this to the audio as well. I can probably use, is it ready? Yeah? No? The sound is not coming. That instead of me explaining you guys what WLO is all about and what we have done so far with WLO, I thought of taking help of my leadership team to explain you the story in a 2 minutes time, but I think we have some technical challenge here. I'm not very sure whether we have solved that. Maybe let's move to the, okay, let me see if some animation is helping.
Right? To get to the optimal well trajectory.
So sorry, but I can go back a slide bit.
WLO, Well Location Optimization, is one of the most valuable and exciting products coming out of Shell's digital program. Getting it right on well count, well configuration, and well location is crucial for competitive delivery.
Multiple reservoir models reflecting the full range of subsurface uncertainties and development options are considered in robust WLO. Ensuing outcomes include high-graded areas in the reservoir that are most prospective for drilling, optimal well count and trajectories, and associated statistical quantifications of recovery performance indicators.
It combines parallel computing, machine learning, and artificial intelligence to get to the optimal well trajectory.
WLO significantly accelerates the field development process by enabling reservoir engineers to explore thousands of well configurations in a matter of a few hours. It optimizes not only the locations, but also the entire trajectory, including smart completions. Optimal well trajectories computed by WLO strictly honor geological and topological drilling constraints and topside facility limits.
WLO is a fantastic digital technology. Application of WLO in the Gulf of Mexico assets has generated significant upside. New projects and infill drilling campaigns increasingly make use of WLO technology, bringing together insights and constraints from geologists, reservoir well, and surface engineers.
Robust WLO technology is designed as an enabler tool for reservoir engineers, and it's applied in integrated workflows. WLO tool covers the entire spectrum of commercial and in-house simulators. There's a great opportunity for Shell and the industry to successfully deploy the technology and add significant value to our operations.
Okay, so I hope that helped a bit. But okay, so what WLO stands for, right? Well location optimization. So what problem we are trying to solve here? So for example, we have a brownfield, few kilometer by few kilometers length. We have a target to kind of drill maybe hundreds of wells in that space. We already have achieved maybe drilled already 20, 30 wells. And now you are supposed to drill the next well. Now the question is, where should you drill next? That's the question we are trying to solve, right? So basically the motivation is, of course, you have n number of possible locations where you can drill and try to figure out which is the best location out of maybe the 30 well drill locations, right? What we try to understand is whether we looked wide enough or whether we can look wide enough, right? So that's all about we are trying to solve in this well location optimization problem. So in the next slide, in the workflow, what I try to help you understand here is the pain points, right? Let's try to understand a bit of a workflow. How does this particular scenario work? What we start with is the P50 based historical reservoir model, history match reservoir model. And basically what you try to do is you forward simulate multiple well location points and try to forecast the production and take a help of various optimizers in a space to figure out whether based on your evaluation criteria or based on your objective functions, whether that is the economic valuation or the NPVs, right? You can see that the cost function on top of is the oil revenue, gas revenue, water production cost, water injection cost, and gas injection cost. That's my cost function. Based on that, I try to decide whether my choice is right or whether I should kind of reiterate my particular entire search, right? So if in this entire workflow, what you probably see, right, number of iterations and then forward simulations, right? In a forward simulation or the forward modeling, what we do, we try to use the physics-based flow simulators to generate the information called the production forecast for many years, right? And that's the time-consuming activity. That takes maybe hours to days, an entire workflow to run, maybe days to weeks sometime, right? So it's quite a lengthy process, and we thought of maybe, can we do this operation maybe in a minimum number of iterations? The job is now, when we kind of think of a different optimizer, job is now, can we reduce number of iterations or can we have a less number of evaluations of simulators to avoid the licensing cost? Okay, so that's about our problem, and let's now try to see whether the Bayesian optimizer is the right choice. What we have seen, the cost of a objective function evaluation, let me go back again. It's not so, okay, so the cost of objective function evaluation is quite high here in the reservoir modeling because it takes hours to days to run your forward simulator, a physics-based simulator, right? Okay, so what we thought, maybe let's try to explore whether Bayesian optimizer is the right choice. Before going to that, right, let's try to understand a bit about, again, this is from this time onward, this slide onward, it will be little bit of kind of a tutorial type of a session for next 5-10 slides, okay? It's a black box optimization. Let's try to understand the black box optimization problem. What do you mean by black box, right? What we have an input and we have an output which we can observe from that function. We have a zero information about the function which we are trying to optimize for, and output is with a noise. So it's very difficult, or there is no possibility of a gradient computation. The functions, the cost functions, or the functions evaluation is a costly, and sometimes the observations are also corrupted with a noise. So this optimization, so how do you basically design and develop an optimization strategy for such black box functions? So what you need to do is, it's a sequential strategical approach we have to take. Just to give you some more familiar example, maybe if reservoir modeling is not so familiar, then maybe these two examples might make sense to you, right? A/B testing and hyperparameter tuning. In A/B testing, what we do is we kind of try to understand the different configurations, and we try to find out the best configurations to optimize our click rate, right, to improve the revenue. In the hyperparameter tuning, there are n number of hyperparameter settings which probably can give you the best outcome or the best accuracy for your machine learning models as well. So these are the examples probably you can quickly relate, comes into this category. Okay, so how do you basically solve this? Even though we know that it's a sequential strategy which we have to implement, basically, how do you basically solve this optimization problem? The target is the global optimization problem. It's a black box objective function, which is expensive to evaluate. As I said, forward simulation of a reservoir model is one of such example. The cartoon picture on the right-hand side basically shows you that, so the dotted black line is your true cost function. The red dots on this black line are nothing but the points which are evaluated, the pre-evaluated. You have information about that points. And what you want to basically know is whether you already have a global optima in the cost function, or whether there is something else, which is maybe a green point, right? And what you see on the envelope around that particular cost function is nothing but the proxy model. So what you try to do in such expensive cost setting, right, where the objective functions are difficult to evaluate, what you try to do is build a proxy. Build a proxy around your cost function, which is cheaper to evaluate, of course, and then optimize the proxy to figure out which is the best optimal point to in that particular true objective function. So two primary questions we need to address here. One, selection of a right proxy model, which model to select, what is the model, and the next, the exploration strategy. Even you have a right proxy model, what is the exploration strategy in that particular proxy setting you will probably find to have a global optima. Okay, so basically it's a typical choice. Most of us basically start with Gaussian process proxy. So there is a reason, because it's a very good proxy for continuous functions, as well as a lot of physical phenomena can be better represented by the Gaussian proxies and stuff like that. So what it is, when you have a finite collection of input points, x1 to xn, what you can probably talk about, the functions evaluated on all those x1 to xn can be represented or in a Gaussian distribution form, 0 mean, and then k is a covariance matrix. You can see that. I just wanted to highlight the K matrix, the covariance matrix. More number of points you evaluate on the cost function, the red point which you saw, the bigger would be the covariance matrix size. I just wanted to remember the size of a covariance matrix here, because this will come in the next few slides about the challenges in also using the Bayesian optimizer, the covariance matrix. Okay, so now you have selected the proxy. Now, what are the different properties this proxy model should have? Of course, it should be observable, you should be able to sample it well, and stuff like that, but also inference in the Gaussian process. Again, I don't want to kind of talk a lot about how do you basically inference that new x point, and how do you basically pick a point evaluation from these joint probability things, but what I want you to remember is the last two equations. When you basically do the inferencing in the Gaussian process, what you require doing later at the end is update your Gaussian process model, right? GP model. And these two equations basically talks about this updation process. What do you see? Matrix inversion. Just remember that. Not too much of mathematics. What it requires in updation is a matrix inversion. And which is the matrix there? Again, the covariance matrix. Okay, so we talked about the proxy. We talked about a little bit about the inferencing strategy and the challenges in the process. What is the exploration strategy which we should be using, right, in this particular scenario? Again, the same cartoon picture on the left. Black dot line is your cost function which you want to evaluate or optimize for. Envelope U is nothing but your proxy, which is a Gaussian proxy. In this case, we have selected the Gaussian proxy. There are n number of possibilities, by the way. And then, okay, so now we want to figure out which is the next point I should be evaluating in this particular cost function. The typical strategy is for initial samples, what you do is you initialize your model and now take a help of an acquisition function. The acquisition function you see on the left below in a green shape, which basically ultimately help you figure out which points to evaluate in the true objective function, right? It's becoming a complex, right? So we basically started with proxy model, which is cheaper to evaluate, and now we have acquisition function to help us with the exploration strategy. Still, we haven't got it very clear probably at this point as well. Let me kind of help you understand this through illustration, right? So basically, again, the same scenario. Blue line is objective function. Gray area is nothing but your proxy. Now the point is where to evaluate. Now my exploration, the acquisition function helped me give the left-hand side corner point to evaluate. I evaluated. I kept on kind of requesting the acquisition function, which is the next point to evaluate. I got a new point to evaluate. After evaluation, I updated my Gaussian process model and kept on doing this process till the time I see that there is basically not so much change in the point which I selected, right? I kind of converge to this point, right? My job here, again, remember, my job here is to find the global optima, not really to fit my proxy well enough to my cost function. That's where you can see that even though I have a right exploration and exploitation strategy, I'm not basically selecting the points on the right-hand side. There is a reason because my global minima lies on the left-hand side, yeah? Okay, so we have seen how does that work, but we still haven't addressed how this exploration, the acquisition function works, right? And how its exploration and exploitation strategy basically works. What does that mean? We try to kind of seek places of a high variance and uncertainty. And in the exploitation, we try to kind of seek with a low mean, right? How do we basically figure that alpha, the acquisition function? Again, there are multiple choices. Again, a bit of the cartoon picture probably, which probably will help you understand better, again, how this acquisition function works. So for example, here again, you have 4 different data points available, which are given from the cost function. What you try to do from your Gaussian proxy, Gaussian process model, you try to sample a function, right, from that particular model. And then what you do is keep on sampling thousands of such functions from that particular Gaussian process. And what you end up is the graph which you see on the top a bit, right? What does it tell you? So basically, if you look, right, the black line is nothing but your the previous minima or the previous maxima, whatever the problem you formulate. And then what you are looking for may be a minima point, and then try to figure out which is the next point I should be evaluating, which will give me the right minima, right? So what we try to solve here is try to understand the expected improvement over the best solution so far. If you look, it tries to basically, if you basically try to count the number of functions below that black line, it gives you the panel, lower panel picture, right? Kind of a histogram, and then that gives you the next point of evaluation. Expected improvement is one of the strategy or one of the acquisition function you can select, or there are other functions also, right? So this particularly help you understand how the acquisition function helps you provide the next point of evaluation. I think with this, let me come back to our well location problem and the challenges we probably faced after integrating this optimizer, right, with a Gaussian proxy and expected improvement as acquisition function while implementing. What you guys must have seen so far, right? So it's hopelessly sequential in nature, this particular method, right? What you do is you basically start with one point, you update your model, you again kind of try to find out the next point of evaluation, and you keep on updating the model and keep on understanding which points to evaluate and keep on iterating. It's kind of a sequential process, right? And that's where what we found. So compared to the particle swarm optimizer, so that's again another statistical global optimizer suitable for the functions like where gradient computations are not possible. So I think compared to that, which is already present in our well location optimization suite, it wasn't really performing to that level, right? From the elapsed time performance perspective because of the sequential in nature. What we use, so we use the open source library PyGPGO, that's in a Python. There is a R package as well available if someone wants to experiment with MLR MBA, which you guys can try. But because of the homogeneity of the entire solution structure, we choose the Python package. So how do you basically make it parallel? The question which we started asking ourselves is, can we evaluate a multiple point simultaneously for a method which is hopelessly sequential, right? And then if we can, then how do you basically, I mean, that's going to defeat the purpose of a model sequential update process, right? And then who can basically give us a multiple points to evaluate? Which is that particular function? How to select which points to evaluate in parallel? So that's another question we need to address. Or should we evaluate the same static number of points in a parallel for every iteration? For example, if you see, right, we started with, for example, 4 data points to evaluate in parallel. Should we have the same 4 number of data points or the cost function points to evaluate in a next iteration also, or should we change that, right? A lot of questions, and who can help us provide those data points as well? So after kind of doing all this research and implementing this particular scenario in parallel, right, what we basically got, right, is very interesting. So maybe I'm kind of coming quickly to the summary part a bit. So if you look at the results, right, so this Bayesian optimization parallel scheme, which basically helped us provide 4 times, which was 4 times faster than our sequential method, which we used in the forward simulation method. It was, of course, 1.2 times faster than the PSO and 2.4 times faster, I mean, basically 2 times reduced the forward simulation. So basically, it not only helped the parallel implementation of Bayesian Optimizer, not only helped us basically get the speed what we wanted, but also number of iterations. So elapsed time also reduced, as well as number of iterations also reduced. If you can see this number, right, on the, this is a synthetic case, which I'm kind of showing, very simple, vertical well, we kind of try to drill through the synthetic use cases, and that's what the example it shows. In the PSO case, particle swarm optimizer, we require basically running the 60 number of iterations, whereas in a BO parallel, Bayesian optimization parallel, we could do that in a 25 iterations only, right? So what it tells, so overall, basically what we can see that it's a efficient optimization strategy for the costly functions, right? It is quite powerful to optimize the complex and expensive black box functions. It has definitely a limited scalability. Probably we didn't talk about the scalability a bit, but as you kind of go more on number of points evaluation, as I said, the variance matrix size becomes larger. The sampling function from the model, the updated model becomes challenging. Updating model becomes challenging and stuff like that, right? It becomes, so basically, if you must have heard, right, the Bayesian optimizer is not so suitable for optimizing the parameter size more than 10, 20, right? So that's the reason probably it's not so, basically, it has a limited scalability. Luckily, we had a minimal number of parameters to evaluate or understand, maybe X and Y location were our parameters, right? But when your parameter size is higher, then, I mean, choose this method wisely, right? Also, you should get your global minima in minimum iterations times, right? So that's another basically challenge. You have to basically play with, again, another set of hyperparameter, like how do you basically select the right acquisition functions? How do you basically strategize your exploration and exploitation strategy to have a minimum number of evaluations for such costly objective function, right? Yeah, so we talked about the limited scalability. So again, the Bayesian optimization is an effective in finding global optima function. That's what we see in the results, from the results as well, and it kind of verifies. With that, maybe from the technology, integration and the results point, I'm done, right? What I want to do now is switch a gear a bit, right? Go back to a couple of initial slides which we talked about, little bit about the organization, right? Sorry to switch gears so basically from heavy technical discussions to the organizational side discussion. So what we do, right, in the what we basically believe in the organization, and in fact everyone believes that data is data enables CI. But what we need is better access to the data, the quality of the data, and well-structured data, right, availability. And then how basically that can be done by adapting the right structure, right tools in a place. To do that, we need to have a right culture and right learning attitude in the group, right? And who can help us do that? Having a right talent in a place. What we are looking for in this particular space is a right talent, people who can understand the data science well, who can build the programs well, who has end-to-end capability of thinking, who has a courage to kind of work in the space of uncertainties and things like that, right? So those are the talents. So yeah, I think world is changing. We also have to change fast along with the world. And now is the time to think bigger. And with that, I will end my talk. Thank you. Yeah. Open for questions, if any. Yeah.
So I have two questions.
Yeah.
So my first question is like, so is this multi-level optimization problem or a single-level optimization problem?
Can you repeat what is?
So is this multi-level optimization problem? So your problem statement does have multiple levels in the data, or is it a single level?
Okay, so if I understand your problem, question correct, right? So what you are trying to say is the level of optimizations,
yeah.
Right? No, it's a single level optimization problem.
Okay.
Yeah.
And second question is like, what are the accuracy matrices in this?
Okay, so I think it's a bit difficult. Basically, what we basically did, right, when we applied the Bayesian Optimizer strategies to our existing well location optimizer softwares, right? So we kind of benchmark that with previously applied the optimizer techniques to find the right global minima, right? To find the right next location, well locations. So and then basically your criteria is always driven by the overall the cost of an objective function, right? And honestly speaking, in this subsurface space, no one knows the truth. It's all uncertain, right? What you try to do is reduce that uncertainty by helping provide a better and better guess. So that's what I would say. I mean, compared with always, yeah, please.